Okay, welcome. Let's go ahead and get started. I noticed Chris, for example, gave a mistake in the book. I think that next time we get together, I will let you know about the errata sheet. So we have an errata sheet that has the corrections to the book. Yes, believe it or not, my book was not perfect, and there were some goofs. So we will talk about that next time. And thank you for doing that. And please, I pay a bounty on any errors that you find in the book that I haven't found yet. So I don't know what that bounty is yet, but we'll figure it out. So with that, let me go ahead and share my screen. And we have a nice picture of Glauco here. How can you make it for Glauco? We're gone now. Okay, so here we are. But before we get started, I wanted to ask if there were any questions concerning the homework and or the review material. Again, I'm assuming the review material is something you will normally look at and look at the solutions and then understand it and be responsible for the material. But I also understand that many times the material isn't totally covered and there'll still be misunderstandings and you'll need elaboration on my part. So I'm happy to do that, but you're going to have to be the ones that ask me about it. So with that, first of all, were there any questions on the review questions? Okay, was there any questions on the homework? Okay, hearing none, I suppose that we'll have that due Monday. I'm willing to postpone if you're having some challenges with the material, but it sounds like we're making headway, and so let's go ahead and continue on doing that. We talked about last time the Fourier Transform. We're looking at the Fourier Transform from a number of different perspectives. Before I go, let me see if I can do something. Oh, there it is. I'm clicking little things on Zoom, trying to get it to do what I want it to do. I don't know. I just see Chris Kappelman here. Okay, we'll go ahead and do it this way. We're talking about the Fourier transform. Anytime you talk about transforms, most of you have had things like Z transforms and Laplace transforms, and I don't know if you've had Hilbert transforms or Henkel transforms or whatever, but the procedure is about the same. You define the transform, then you define a bunch of properties of the transform, such as in our case with the Fourier transform, the Fourier scaling theorem, the shift theorem, and similar sorts of things. And then once you do that, you define some transform pairs, be it in the Laplace transform domain, the Z transform domain, or whatever. So we're still going through that. And last time we kind of ended up here. Let's go back one to kind of remember where we're exactly at. We talked about the scaling theorem before. And the interesting thing about the scaling theorem is the derivatives. And hopefully you took a look at that problem and understand what that problem is. I forget which one it is in the review section, but there was one there where I asked you to look at the delta function of something like the cosine of G of t in general. Well, we're not starting off with good penmanship here. Let me see if I can do better. I don't know if any of you guys have ever worked on one of these pen things, but it's very, boy, look at that. Let's see if I can do it up here again. Del of G of t. And so the question is, what is a Dirac delta of an arbitrary function? And this indeed does come up in communication theory, and so it's a useful property. So with that, there was that problem. I hope that you've looked at it. I hope that you understand it. If not, please bring it up in the subsequent session. If you did understand it, I think that's great, and we can move on. Here's another Fourier transform pair, and that is that the exponential Fourier transforms to the delta function. We know that delta t, here's the way we know that. We know that delta t has a Fourier transform of 1. From the duality theorem, then, it corresponds that 1 as a Fourier transform of delta of u. We also know that del of t minus tau has a Fourier transform of e to the minus j 2 pi u tau. So if we look at the Fourier dual of this expression, we get that the left side, e to the j 2 pi, we use the variable c of t, Fourier transforms to del of u minus c. So the relationship between here and here is direct application of duality. Because if a shifted delta function Fourier transforms to a exponential, I forgot my u out here, didn't I? If it Fourier transforms to a linear phase shift, then a linear phase shift in time should correspond to a delta of u minus c. Now this is really an intuitive property. What is this? This is a sinusoid. It's a complex sinusoid, isn't it? This cosine plus j sine. And so this is a cosine of 2 pi ct plus j times the sine of 2 pi ct. And we can see, interestingly, that there's only one frequency. C here has units of cycles per second. It has to. Remember, all of the arguments of exponentials must be unitless. So if this has units of time, then C must have units of 1 over time, because the overall exponential must be unitless. So this has a, this of course we know is a sinusoid with a frequency of C cycles per second. By the way, the mathematicians, I know a guy in the math department that pronounces this to C. He puts a T in front of it instead of like the third letter of the English alphabet, just calling it C. I've always called it C, but if you like C, that's fine. Well, we know that this is a sinusoid, and this is only one frequency, and this is a sinusoid, and it's also of one frequency. So it makes total sense that if we look in the frequency domain, that the frequency domain is only going to have a single frequency component. And that frequency component, that's supposed to be a direct delta. That single frequency exists as a direct delta at the frequency of C. And that's indeed what we're seeing here. This is a sinusoid, has a Fourier transform of a shifted direct delta in the frequency domain at the one frequency that the sinusoid is at. So this makes a lot of intuitive sense as a Fourier transform theorem, or a Fourier transform relation. One of the cool things about this is it exposes something interesting in terms of the Fourier series. In terms of the Fourier series, it means that if you have a Fourier series, it manifests itself in the frequency domain as a bunch of direct deltas. We all know that this is the expression for the Fourier series. We've seen this before. Now, if we Fourier transform it, the Fourier transform of x of t is the Fourier transform of the stuff on the right here. It's the Fourier transform of all of this stuff. Well, what is all of that stuff? All of that stuff is nothing more than the following. We can take the Fourier transform operator inside the summation. Because Fourier transform is a linear operation, it means the Fourier transform of the sum is the sum of the Fourier transforms. We can take the Fourier transform in front of the C sub n. Why is that? Because the Fourier transform operator only operates on functions of t. This is not a function of t. So therefore, we can take the Fourier transform operator inside, we can move it from the left to the right of C sub n. And we're left with the Fourier transform of this thing, e to the j 2 pi nt over t. And we've just seen that this Fourier transform is to a shifted direct delta function. Well, this is kind of cool because this tells us something that we probably already know. It tells us something we already know, that if we have a Fourier transform here, the periodic function, where I go trying to do my periodic function. This is x of t, this is a periodic function. And we know that this periodic function is totally determined by the C sub n's. It's totally determined by the Fourier series coefficients, at least in the sense of a Gibbs phenomena sort of result. So this is a function of t. We also know that when we do the Fourier transform or the Fourier series, that we have harmonics. Now this is an interval of t. And notice we're keeping things simple. It's just an interval of t. We're not dealing with 1 over t as the frequency and things of that sort, which is often confusing in Fourier systems, Fourier series theory. But we know that, interestingly, in the frequency domain, what this expression says is that we have a bunch of direct deltas. And these direct deltas are equally spaced. And the separation between the direct deltas is 1 over t. So that's because all of the direct deltas live at u is equal to n over t. So 1 over t, 2 over t, 3 over t, etc. And so this is in the frequency domain. So this is the Fourier transform of the Fourier series. And what we get is something interesting. We get the Fourier series coefficients. This direct delta at the origin, for example, is C0. That's the DC value of the Fourier series. And that's what we have here. That's the DC value. We have a C sub 1 here. That's the fundamental frequency. We have C sub 2, which is the first harmonic. We have C sub 3, which is the second harmonic. Now, because of the weirdness of Fourier transforms, we have a C minus 1 here, and we have a C minus 2. And so all of these Fourier series coefficients in the Fourier series are manifested by weights to direct delta functions in the frequency domain. And that's a very nice way to remember that here we have all of the harmonics. Here we have all of the harmonics, and the weight of the direct delta function is C sub 1, C sub 2, C sub 3. By the way, what does this mean, a weight of C sub 0? Does this mean that the direct delta has a height of C sub 0? No. Or C sub 1? No, it doesn't mean that. The height of this direct delta function is infinite. What it means is the area under this direct delta function is C sub 1. That's the area under the direct delta function. So that's what we mean in such cases. One of the things I didn't address, and maybe we should talk about it now, is something which is always puzzling. So this is kind of a side. So this is kind of a side. We have a Fourier transform. The Fourier transform is always bilateral in the sense that, well, there's exceptions, but in this case, we have negative frequency. What's the deal there? What's the physical manifestation of negative frequency? What is a negative frequency? I used to joke that a positive frequency is when you whistled in or when you whistled out, like, and a negative frequency is when you whistled in, like, but that's a joke. There is no actual idea of a negative frequency. And the concept still escapes me. I don't know what a negative frequency is. And I dare say that most people that are into Fourier analysis won't know what a negative frequency is. But nevertheless, we use them because of the utility. It's just a very interesting artifact of the Fourier transform. And it turns out not to get in our way. So we won't let it get in our way. So I did want to mention this as a side of negative frequency. And exactly what that means. Okay, let's go on to the next slide. Yes.
I have a question.
Sure.
So I was actually going to ask about the Dirac delta and the constants in front, but you answered that. It has to do with the area. It doesn't change the height of it.
Yeah, the height is still infinite, yes.
Yeah, but my question is, you know, when we graph it, we don't really show like the area under it, you know, it's kind of just a straight line all the time. So my question is, what's really the functional difference between a Dirac delta function, let's say with an area of 1, and a Dirac delta function with an area of 3 or something like that? Like,
Yeah, that's an excellent question. I think, Aiden, what we do is kind of dictate the area under the delta function in an indirect way by the height of whatever that arrow is. So you notice that the C0 has a height which is different than the C1. Now, both of them go to infinity, but it's just kind of a way to code that the C sub 0 has a bigger area than the C sub 1. So we kind of modulate it that way. It's just a way of expressing it. Does that answer your question?
Yeah, that makes sense. And so when you're graphing it, you do graph them shorter if they have a smaller area.
Yes.
Okay, that makes sense. But then when you actually get around to using a Dirac delta function for any reason, like what really is a difference between one with a bigger area and one with a smaller area?
Well, it's simply the difference between the bigger area and the smaller area is just manifest in the math. You have, for example, the integral of a delta t. The area of a delta t is equal to 1. The area of a constant times a delta t the area under a constant times del of t is equal to c. So you just carry the c along with your notation in the mathematics. And if you place it there, everything is going to work out fine.
Okay, sounds good. Thank you.
Okay, very good. Very good question. Okay, any other questions on this? Now, Dirac delta is a weird animal. As I said, there's no way that you can go into the lab and generate a Dirac delta. You just can't do it because it's going to have an infinite energy, and infinity, this is a topic for a whole lecture sometimes, infinity does not exist in our universe. There's no place where there is an actual infinity. There are conceptual infinities. We can think about infinities in our mind, but if you talk about a physical manifestation of an infinity, it simply doesn't exist. You break into incredible absurdities if you assume infinite things. But nevertheless, the world of math, and especially of Fourier analysis, it's still nice to talk about. It's a wonderful bookkeeping sort of technique, recognizing that indeed that we can use these delta functions very nicely in terms of mathematics. Many times, well, yeah, here's another property. I'm sorry, I had about 2 or 3 thoughts going through my head. Here's another thought about the Dirac delta. So this is kind of a side too. Many times we like to talk about the step response, or a unit step function. We haven't defined this yet, but a unit step function is something which is 0 for negative time and it's 1 for positive time. And we can talk about the derivative of the unit step. Well, if you go back and you take your calculus class, they will say that the derivative of the unit step is not defined at t is equal to 0. No, that's not true in engineering. The derivative of the delta of the unit step is a Dirac delta function. And anytime you have a discontinuity and you take the derivative of it, you get a unit step. Now let's go backwards. If we integrate, can we integrate this unit step and can we integrate this Dirac delta and get the unit step? And the answer is yes. We integrate up to this point and we get 0, right? We integrate up to this point and we get just right before the origin and we still get 0 because that's the area. We integrate just a little bit beyond the Dirac delta and all of a sudden the area becomes 1. The integral from here all the way up to here is still 1, so it stays 1. So we see we have a consistency here in terms of taking the derivative to get the delta function, and then even going backwards to get the unit step from the delta function. And therefore, any time that you have a signal, and that signal would have discontinuities, that discontinuity would differentiate into a Dirac. And what is the Dirac delta? We add another sheet here. What is that Dirac delta? Suppose you had a function now which was x of t. And there was a discontinuity jump here. So this was the function of x of t, and let this discontinuity jump be, let's let that distance be a. That's the distance from here to here. So this is x of t. What would the derivative of this look like? Well, I don't know if I can draw the derivative. I'll pretend I can draw the derivative, except for the discontinuity. I guess the is negative. But at this point where the discontinuity is, let's call that tau. There's going to be a Dirac delta there because of the discontinuity. Anytime you have a discontinuity, there's a Dirac delta in the derivative. And we would say that Dirac delta for this specific point, if it existed at tau, would be equal to a times del of t minus tau. So the rest of the derivative is what it is, but at the discontinuity, the Dirac delta, the derivative is equal to a, whatever this length of the discontinuity is, and times the delta function located at that point. So that's a nice interpretation of a Dirac delta from an engineering perspective. And I think mathematicians still like, as far as I know, they still don't like the idea of taking a derivative at a discontinuity. But for us, it's very satisfying, and it works very well. Do Dirac deltas ever give you problems? I will tell you the only problem that ever happens that I have done in my entire career is as follows. This is the only problem with the Dirac delta. And if you run up against this problem, you got to say, okay, I got to go back and I have to do something different. I have to do something different because I've screwed things up. Suppose you have a delta function at the origin. What is the integral from, say, -1 to 0 of the delta t? So you're integrating here from -1 to 0 of the delta t. And what is that equal to? there's a problem. And the problem is, do you include the Dirac delta at the origin of the integration? Do you include half of it? Do you include all of it? What's your definition? What do you do? The answer is there is no answer. There is no answer because suppose I define my Dirac delta as the limit of this as, and this is from 0 to 1 over t and a height of t. So I'm going to say the limit of this is t is equal to 0. That could be a definition of a Dirac delta function. Then the integral from minus 1 to 0 is going to be 0. But what if I define it this way? What if I define it from minus 1 over t? To 0 with a height of t. Then my answer is going to be 1, isn't it? If I define it as the way we initially did, as from centered about the origin, it would be a half, right? So all of these give different answers. All of them give different answers. This one gives a value of 0. This one gives you a value of 1. And if we use this one, we give a value of 1/2. So the point is that this has no answer. So the only problem I've ever encountered with Dirac deltas is when they exist at the end of an integration point. And you need to go back and you need to define things. If you remember Laplace transform, they would always do the integration from 0 minus to infinity. I don't know how you were taught Laplace transforms, but it was always 0 minus to infinity. So this means you always include you always integrate just an epsilon to the left of the origin. See, in this case, if I integrated from minus 1 to, I'm going to call it 0 plus, in other words, just to a little bit to the right of the origin, and I was to do this with a del of t, this would be equal to 1 because I'm saying I'm always going to include the total origin. But in general, if you don't have notation like this, if you don't have a clear idea of what's going on there, you can't perform the integration. If you ever get to that point, you've screwed up with the math, you have to go back, you have to look at your problem, and usually the context of the problem will reveal your problem in coming up with such a unresolvable paradox. But every place else, the Dirac delta works wonderfully and beautifully, in my experience. Okay?
Dr. Marks?
Yeah,
Looking at the discontinuity problem there, what if the discontinuity is downwards? Would it be a negative Dirac delta function?
that's an excellent point, Adam. The A is direction. And let me get a new slide. Yeah, that's an excellent point. If your discontinuity goes down, then you would have to include the value. Say this was -7, and this occurred at tau. The derivative here would be del -7 del of t minus tau. So that's an excellent point that completes this thought. Is that, yeah, if we go down, it's a -7. So the direction of the discontinuity is important. Okay. Another good question. Any other comments? Okay, if not, let's go on to a very beautiful function. It's the sinc of x. You've all seen this, and you've seen it defined probably in different ways. We're going to define it in the most beautiful way possible. It's a beautiful, beautiful way of doing it. It's the sine of pi t over pi t. We've all seen sine x over x. Usually it's your first Fourier transform. There's a reason that we do this, and one of the reasons is that the sink of the origin, you can see, is equal to 1. The sink of the origin is equal to 1. So that's kind of cool. You remember that it always goes through 1. The other thing is that the sink of n is always equal to 0 as long as n is not equal to 0. So you can see the 0 crossings here. The 0 crossings are at 1, 2, 3, and 4. And -1, -2, -3, and -4. So that's a beautiful way to think about the sinc function, the sine of pi x, pi t over pi t. And so it has that property, you know the way that the sine x over x wiggles, but here you know it's equal to 1 at the origin, and all of the 0 crossings go through integers. And as you probably know, what is the Fourier? Well, here's another reason, which is, no, I guess, never mind, we haven't got there yet. I'm giving you a non-causal comment, and I don't want to give you non-causal comments. Okay, so that's the sinc. And we're going to define another function here. We're going to define a Chronicler Delta. Now, the Chronicler Delta is the discrete equivalent of the Dirac Delta, named after a guy named Chronicler who believed that God made the integers and man made all the mathematics that came from the integers. That's what he was famous for. But you'll notice the similarity with the Dirac Delta. The Dirac Delta is equal to 1 for n is equal to 0 and 0 otherwise. So if we were to plot this in discrete time, we would have 1 at the origin, and we would have 0 at all of the other values that were integers. So again, you can see that it does have the flavor of a Dirac Delta in the sense that it exists somewhere and it doesn't exist other places. The interesting thing about the sinc of t is that the sinc of t is equal to a Chronicler Delta. Notice that the sinc of t, what's the sinc of 0? The sinc of 0 is 1. What's the sinc of 1, 2, or 3? It's 0. So the sinc of n is equal to the Chronicler Delta. Very interesting property. And it's, I will point out this is a beautiful definition of the sinc function because it maintains this property. It's easy to remember, and you kind of know what it wiggles, kind of looks like. You can fill in the details later if you need to. Then we have the rectangle function. This is the rectangle function. The rectangle function is denoted by a capital pi, and you can guess why we use the capital pi, right? Because it kind of looks like a rectangle. And the capital pi of t is equal to 1 for t is less than 1/2. Now it's the magnitude of t is equal to less than 1/2. And if you have a challenge unwrapping the magnitude, it's what's represented here to the left in terms of figure. It's equal to 0 outside that interval. So outside the interval, it's equal to 0. And it's equal to 1/2 at t is equal to 1/2. Now this is curious. This is very curious, and for engineering applications, you will never ever be concerned with this, I don't believe. But here's the reason that we define it as equal to 1/2 for t is equal to 0. If we take a Fourier series and we experience Gibbs phenomenon, you know Gibbs phenomenon? And we experience Gibbs phenomenon, which I'll try to do here. Wiggle, wiggle, wiggle up here and then down here. Okay, here's the point. If you do a Fourier series, you not only have Gibbs phenomena where these little wiggles don't go away, they kind of crush in from both sides. But the other thing is at the point of the discontinuity, we always get a convergence to the arithmetic mean point of the discontinuity. So in a Fourier series, we always have, or in a Fourier transform also, we always have this midpoint occurring. This is interesting because Suppose we take a rectangle of T. But we don't call it a rectangle. We're going to take the point at 1/2 here. And we're going to call that 2. Just for one point. One point, we're going to call it 2. And for this one over here, we'll call it 3. So it's equal to 1 here, it's equal to 0 outside. At this discontinuity, it's equal to 2. At this other discontinuity, it's equal to 3. Now here's the thing, when you take a Fourier transform, you're integrating over x of t, e to the minus j 2 pi dt. Right? This is a little method in mathematics that mathematicians like. If you're integrating over x of t, what is the area under a single dislocated point? Anybody hazard a guess? 0, right? Because it's the area under the point. What's the area under a point? As a single value which is dislocated up here. The area of that is going to be 0. So therefore, I don't care where you put the points at plus, minus 1/2, and plus 1/2. The results are going to be exactly the same. They're going to be exactly the same because you're integrating over something which has no area. But here's the interesting part. If you Fourier transform that into the sink, and you do the inverse Fourier transform, well, clearly the Fourier transform loses the points of discontinuity. It's not resident in the sin x over x. So that's totally lost. So the question is, what happens when you inverse Fourier transform? When you inverse Fourier transform, the inverse Fourier transforms put these points of discontinuity at the arithmetic mean point. So in this case, 1/2. So that's the reason we do that, for kind of consistency. And it does turn out that if you have a signal with a discontinuity, and that signal comes along, and then it does something, and then it does something else, x of t. It doesn't matter what the value of the discontinuity is. But if you Fourier transform it, and then you inverse Fourier transform it, guess what you get? You get the arithmetic mean point. You get midway between the discontinuity. So this is a point, again, primarily for mathematicians. We know as engineers, we don't deal with displaced single points. It's more of a mathematical construct. But in doing a little kowtowing to the mathematicians, we include this idea of at 1/2 t is equal to 1/2, because that's what would happen if we took this rectangle, we Fourier transformed it, and then we inverse Fourier transformed it, we would get back the midpoint. And that's interesting. So this is the rectangle. Everybody knows that the rectangle Fourier transforms to the sink. That's probably your first Fourier transform as an undergraduate. The rectangle Fourier transforms to a sink. The beauty of what we have done is we have defined the rectangle in the sink so that the Fourier transform relationship is exact. The rectangle function Fourier transforms exactly into a sink function. And we know by duality, we know that the sink of t Fourier transforms to a rectangle function in U because of duality.
Sorry, how do we know that they are they form a duality?
Well, everything forms a duality. Anytime you have a Fourier transform pair, if you remember, a rect transforms into a sinc. Duality says a sinc will Fourier transform into a rect. That's the duality theorem. If x, the duality theorem says that if x of t transforms to x of u, and we're a little bit sloppy with our notation because usually we do a lowercase for time domain and uppercase for frequency domain, but here we're going to abandon that. And we're going to see that x of t will Fourier transforms to x of little x of minus u. This is duality.
Okay, so that's true for all Fourier.
That's true for all Fourier transforms. That's right.
Cool.
So again, anytime you have one Fourier transform, you have two, because you can always apply the duality theorem and get kind of the flip-flop using the duality theorem. So if a rectangle transforms into a sinc will Fourier transform into a rectangle. Any other questions? Then there is the Siegen function. Now this is very interesting. The Siegen function is an acronym for, let's start here. Is equal to the sine. So instead of saying this should be the sine of t, but we took out the I and now it's called the Siegen of t. And the reason it's the sine of t, if it's equal to -1, if it's negative, it's equal to +1 if it's positive. And you can see in deference to our mathematics that if we have a midpoint here, we call it equal to 0. It's midway between the two discontinuities. Now you notice we pronounced S-I-G-N as Siegen. Can anybody guess why we don't call it? Why don't we just call it the sine, the S-I-G-N of t?
We already got a sine function.
We already have a sine. That's right. We have a sine, and we don't want to mess around with confusing the sine with the Siegen function. So that's the reason that we call it the Siegen function, which is, it's the way it is, right? It's a little bit of historical inertia. Now, the Siegen function we show in the book is equal to 1 over j pi u. So that's the Fourier transform of the Siegen function. And I won't go through the proof here. It requires use of a limit. And it is in the book in this section. And you can see up here that I always put in the section. It's in section 2.3.5.5. So you can always refer to there for the different results, or the different proofs or elaboration on some of the ideas that I present. We've used this before, but now we're going to use the unit step. We're going to do the unit step in terms of the signal. Think about this. If you take the signal, which looks like this, you add 1. What happens if you add 1? You add 1. You add 1, you get this result, right? This is the Siegen function plus 1. It goes up to 2 now. So this is the Siegen function plus 1. All that remains to do is divide this by 2, and you have a unit step, don't you? So we're going to take the secant function, we're going to add 1, and we're going to divide by 1/2, and we get the unit step. So that makes a lot of sense. The reason we like to define it this way is that we already know the Fourier transform of the secant function, and so this will allow us to get the Fourier transform of the unit step. Just aside, a property that we're using here is linearity. Linearity says that I'm going to use a Fourier transform operator. The Fourier transform of A times x of t plus b times y of t. And hopefully you've seen linearity in your systems analysis. The Fourier transform is a special case of this. Is A times the Fourier transform of x of t plus b times the Fourier transform of y of t. That's the definition of linearity. So there's two aspects to it. One is the homogeneity property, which says that the Fourier transform of A times x of t, and these are just trivial to prove. You just plug them into the Fourier transform definition, is equal to A times the Fourier transform of x of t. This simply means if you multiply or amplify a signal by 7, you amplify its spectrum by 7, right? That's all that means. The other one is, let's see, homogeneity, and the other one is additivity. Additivity says the Fourier transform of x, I'm not going to put the plus t, just for sake of brevity. It says the Fourier transform of the sum of two functions is equal to the sum of individual Fourier transforms. These two properties together, if you recall, define what we mean by linear. If the operator is homogeneous and it displays the property of additivity, then it is said to be linear. This relationship incorporates both homogeneity and additivity into a single expression. So this expression has both the homogeneity aspect and the additivity aspect. And so it's all encompassing for the necessary and sufficient condition for linear. That's a definition. So what does that mean in our case? It means that we can take 1/2 times the Fourier transform of secant of t plus the Fourier transform of 1, and we can get the Fourier transform of the unit step. And that's what we're going to do here. The unit step is equal to this, is equal to 1/2 times the Fourier transform of 1. Well, the Fourier transform of 1 is delta of t. We know that because we have already shown that del of t has a Fourier transform of 1. So by duality, 1 has a Fourier transform of del of u. Guess what? You see the typo here? I have a typo. This should be del of u, shouldn't it? Try that again. I didn't succeed very well, but that's a typo. That should be a u. Does that make sense? And so here we have the Fourier transform of a unit step. Let's look at the Gaussian now. The Gaussian is fascinating because you're familiar with it in terms of probability. And chances are you did not see the Gaussian in the area of undergraduate education. in the area of signal analysis. But the Gaussian is very important function for a number of reasons. It's our mathematical friend, and if you take probability, you'll find out that we love Gaussians because Gaussians are everywhere. They're just ubiquitous all over the place. But suppose you had an e to the minus pi t squared, and there's a reason that I do this. Remember, we're trying to define these terms in ways that it's easy to remember. And we want to easily remember these terms. Well, guess what happens? The Fourier transform of a Gaussian is a Gaussian. And it's exactly the same Gaussian. So if you ask yourself, what is one thing that Fourier transforms and you get the same thing back? The answer is a Gaussian. It turns out not to be the only thing that Fourier transforms to itself. We have something which we will not cover called Hermite polynomials that have the same exact property. But for our purposes, this is the only auto one that we'll use. No, there's another one, the Coleman function. When we get to the Coleman function, which we have not gotten to yet, we'll see that that's also its own Fourier transform. So again, the Gaussian is very beautiful in the sense that e to the minus pi t squared Fourier transforms to e to the minus pi u squared. And why is that pi there? That pi there is to make the transformation beautiful so that the x of t has the same exact form as the u of t. We don't have to worry about any scaling things happening. Now we come to a fun one, which is the Coleman function. The
Mark,
Coleman, yes.
is there not a like a way to like how to like call the Gaussian function, like the unit step has like u of t or signum has like sgn of t?
Oh, in other words, are you asking, could we define another function, e to the minus pi t squared as a unit step? Is that what you're asking?
Or no, I mean I don't know. I guess it just you just write it out as e to the minus pi t squared, not like doesn't have like some kind of fancy name for like sgn of t. You could call it.
Okay, I'm not sure what you're talking about, Justin. One of the things that I did here is I just only showed half of the Gaussian. It's confusing. But the Gaussian that we're talking about, Fourier transform, actually goes from minus infinity to infinity. Was that the source of confusion? Or?
I think I got it now.
Okay, yeah, that's the point. So the transform pair, and thank you for pointing me. Here's the thing. This is e to the j 2 pi. That's equal to e to the minus pi u squared. Does that make sense? So the integral is from minus infinity to infinity. I don't know why I put parentheses around the u. I felt very protective today. But that's the Fourier transform that we're talking about. Notice something interesting here. I think it's nice to tie in some of the things that we talked about here. Can't we write this as follows? Couldn't we write it like this? Yeah, we could write it like this, just expanding the e to the j via Euler's formula. Is this function the cosine of 2 pi, is this even or odd? It's even, isn't it? The sine is odd, right? What about this e to the minus pi t squared? That's even, right? That's very evident with the plot that we see here on the top. Okay, what is an even? Okay, what is an even times an odd function?
An odd.
An odd, and what's the area under an odd function?
0.
0. So therefore, because of that, I don't have to consider this sign at all. Does everybody follow that? E to the minus pi t squared is even. The sign is odd. Even times an odd is an odd function, and the area under the odd function is 0. So therefore, I can totally disregard the sign. Is that okay? In fact, what happens if you multiply I see a little bit of this, little bit of. This is an e to the minus pi t squared, right? I'm going to multiply it by a sign. I don't know what it looks like, but I'm going to end up with something that looks like this. I'm going to end up on the right side. Hopefully that sinusoid started at 0. On the right side, I'm going to have something which looks like this. And on the left side, I'm going to have something which looks like this. Right? When I multiply the two together. So again, this is even. This is odd. When we multiply an even times an odd, we get an odd. And here's the cool part. Area-wise, this part eats up this part. This part eats up this part. This part eats up this part. And we see that everything from negative infinity to 0 eats up everything from 0 to infinity. So that's a pretty cool result. So therefore, the e to the minus pi t squared times the odd function of the sign is going to integrate to 0. And we're just left with, this is equal to which is pretty cool. That's a simplification of the expression, isn't it? But this is even. Isn't that the same thing as twice the integral from 0 to infinity? And if you have an even function, you just have to integrate over half of it and then double the results. So you can see here the utility of using the idea of even and odd. And all of these expressions integrate to e to the minus pi u squared. So that's a little side on the idea of using even and odd functions to simplify and manipulate Fourier transforms into different expressions. See, I think if you were presented with this, and we're gonna see a case where we're presented with this, that one could work backwards. If you were getting this, could you compute the Fourier transform of e to the minus pi t squared? You can go backwards, and you can say, yeah, you know, that's equal to from the unilateral to the bilateral integration. And you know, if it's here, I can add in the j sign, and when I add in the j sign, that becomes the definition of the Fourier transform. So when you see integrations that have cosines, even functions, you can always stick in the signs and things and go backwards from the mathematical expression to the expression for the Fourier transform. That's kind of interesting. It's kind of inverse engineering. Any other questions on that? Okay, this will probably be the last one that we talk about today, which is the Coleman function. You can see it's a sequence of Dirac deltas expressed, as you can see here, and separated by integer values. Did you see immediately why it's called a Coleman function? Yep. You can see immediately why it's called a Coleman function, because it looks like a comb. And it's an infinite series of Dirac delta functions. Here's the interesting thing. Just like the Gaussian, the Coleman function has itself as the Fourier transform. It isn't obvious, but that's what happens. The Coleman function has itself as a Fourier transform, just like the Gaussian. And we can prove this by as follows. The comb of t can be written as a summation of a Fourier series. And what are the coefficients? The coefficients are equal to the integral over a period of the original function times e to the minus j 2 pi u t over t. You should remember this equation, right? It's the integral of the comb. But we want to integrate over a period. So what period are we going to integrate over? We're going to integrate here. We're going to integrate from minus 1/2 to 1/2. And what is the comb function between this interval?
The Dirac delta.
It's a Dirac delta, that's right. So in this interval from over a period, the Coleman function is just equal to a Dirac delta over a single period. That's right. And we're left with this. And we know by the shifting property of the Dirac delta, this integrates to what?
E to the minus j 2 pi times 0 over t.
Which is, what is e to the j 2 pi u 0 over t?
1.
Yeah. Exactly. We know by the shifting property that this is just equal to 1. Remember the shifting property, you get back this evaluated where the argument of the delta function is 0. So this is t is equal to 0. So we get back this expression evaluated at t is equal to 0, which is 1. So this is fascinating because it says that the comb of t is equal to the summation of n is equal over all n. I'll just put all n here. Of c sub n times, or I'm sorry, we've already determined what c sub n is equal to 1 times e to the j 2 pi ut. So if you've ever wondered, I don't know if you've wondered, but I've wondered, what is the Fourier series when all of the Fourier series coefficients are 1? Now we know, if all of the Fourier series coefficients are 1, then that's the Fourier series of a Coleman function. We've just shown that, and I think that that's really fascinating. So with that, then we can Fourier transform it. Again, Fourier transform is linear, so we can take the Fourier operator inside the summation sign. And so we have the summation over n, and what's the Fourier transform of this? Remember the shift theorem, the exponential Fourier transforms to a delta function? It's something we saw earlier today. And lo and behold, what is this? That's the Coleman view. So we see, as promised, the Coleman of T Fourier transforms to itself the Coleman view. And we've run across two of these strange entities today for the Gaussian and the Coleman function. Both have themselves as their own Fourier transform. Okay, any questions at all? Okay, hearing
I have a
none.
question.
Yes.
I have a question about something.
Yeah,
So before the next homework, I was hoping you could briefly remind me, like what convolution?
convolution.
Yeah. Yeah, what convolution is, because from what I remember from undergrad signal processing classes, is that all I remember is the having to do the annoying shifting and
The shift and flip, yes.
yeah, that's all I remember, and I don't think that's actually going to be helpful. So I was hoping you could just remind me conceptually what convolution does.
Okay, let me ask you this. Instead of kind of hopping around, which problem is giving you challenges, or is there one that's giving you a challenge?
So I haven't started the homework, but just looking at it, I see some convolution, and I think that you've given us enough theorems and properties that will like help me be able to work around that, but like that I still don't understand conceptually what convolution is. So it's not any particular homework problem that I've started that's giving me a problem. I just don't know what it is, and I'd like to actually know what I'm doing instead of just applying theorems and not really understanding.
Sure. Okay, so let me give you what I think you should know about convolution up to this point. You should know, of course, like you say, the convolution of it. That's the definition of the convolution integral with the flip and shift. You should know some convolution algebra. For example, convolution is commutative. Well, before that, let me just remind us that this is Fourier transform to y. And I'm going to suppress the arguments here, if that's okay. But y is equal to the Fourier transform of x times the Fourier transform of h. Now, h in system theory is sometimes called the transfer function of the system. But y is equal to x times h. So convolution simplifies in the Fourier domain to multiplication. There's a few things which are useful in convolution algebra. First of all, convolution is commutative. So you do have an algebra because both of these Fourier transforms to x times h, right? And so just like in the Fourier domain, we have commutativity. We also have Fourier. We also have commutativity with the in the convolution domain. Another thing is that x involved with say h plus k is equal to x involved with h plus x involved with k. And we see this immediately. This might not be obvious from the convolution algebra, but we see it immediately when we do the Fourier transform, because the Fourier transform is x times h plus k. And so we see these obviously proved in the Fourier domain. So it's x times h plus x times k. Right? So it is commutative. It's distributive. It's associative. What do I mean by associative? Some constant times I don't know what I mean by associative. Kind of thing. Okay, we'll leave that for later. Associative. What's associative? Remind me what associative is in algebra. Adam is
It's like distributive, except you can.
Okay, you cut out.
You
You
can.
you can do the parentheses in any order.
Yeah, yeah.
Oh, okay, of course. X convolved with K convolved with H, there you go. Is equal to X convolved with K convolved with H. And these are obvious because each one of those multiply or Fourier transforms to X times K times H. So it's also associative. The cool thing to remember is the special cases, which is the direct delta. That X of t, this is the shifting property, X of t convolved with delta of t minus tau is equal to what? X of t minus tau. So this is where we say if we have an X of t, we convolve it with something with a delta function that's here, say it's some value of tau. We're going to receive a value here which is similar to tau. We take this base signal and if we convolve it with the delta function, we get there's this, I think I called this the shifting property. That's not the shifting property. The shifting property is that the integral of x of tau and still is tau. And d tau is equal to x of t. So I think those are the rules of convolution that should help. The first one is just convolution algebra. The second one is the dandiness of the Dirac delta in the convolution algebra. The Dirac delta allows you to get rid of integrals, as you see in the shifting property. Notice if you have a Dirac delta that's in the integral goes away. That's nice, you get rid of it. And the other thing is this idea that if you involve something with a shifted Dirac delta function, you move the function to be centered where the Dirac delta function is. Hopefully this should help.
Yeah, it will. Thank you.
Okay, great. If you have time enough to copy it down to your satisfaction?
Yes, sir, I did.
Okay, fine. Any other questions?
Yeah,
Yes.
I had a question. So a little bit on this topic. How would you do the convolution between two delta functions? Would you just treat the first delta function as the x of t?
Yes.
Kind of.
For the problem that I gave you, the hint is to use the shift theory. Treat one of them as this delta t, take the x of t as the other delta t, and it should pop right out. The answer is another delta t, but you just have to figure out where that delta t is.
All right,
I mean,
thank you.
if you look, if you have this delta t like here, if you have just a delta t, and you convolve it with a delta, it was a little sanity check, delta t minus tau. According to what we just thought of up here, what's going to happen? It's going to take the baseband and it's going to center it here. So we're going to take the baseband and we're going to center it here, and we're going to get, if this is a some value of tau, we're going to get this delta function shifted to where this should be. So we do get another delta of t minus tau. Does that kind of help, Justin?
Yes, thank you.
Yeah, you're exactly on the right track. Any other questions? Okie dokie. Well, today is what day? Thursday? And so the homework, since you seem to have a good handle on it, will be due in box by Monday. And when I say Monday, I mean late state. And so we will see you again then next week on Tuesday, and we will continue and maybe even finish off with the review of signal classes in Fourier Transform theorems and Fourier Transform pairs. And what we're doing here is we're building a toolbox. This stuff might seem inconsequential now because you don't see where we're going to use it, but we're building a toolbox which we'll be able to use for analysis and synthesis of signals in some very interesting engineering problems later on. And they are going to require a mastery of this material, as we talk about. So that's the reason we're doing this stuff. Okay. Thank you for your time, gentlemen.
Thank you.
Thank you.
Hi, everyone.
Hey, Dr. Marks, I had a quick question.
Okay, just 1 second. I want to do this off screen here. Tell you what, log back in. There's a reason. Log back into the same place with